let's assume it's 5:45 in some place of the world, for sure it is, or with some clocks. So our next speaker is Emily King, who actually knows Buenos Aires, as not most of the speakers so far did. She came and visited us in person. She visited Victoria Paternostro, with whom she works. And she's talking about some topics in harmonic analysis over locally compact abelian groups.
Yeah, thank you for the invitation. I wish I were enjoying delicious steak and ice cream and Malbec rather than staring at a Zoom screen, but this is the life that we live these days. Yeah, so my plan is to try to like keep this sort of maybe shallow, maybe hopefully give you some inspiration to look at some of the papers, but I have a ton of hidden slides at the end. So if you have any questions, I might already have a slide with more complicated looking slides hidden at the end. Okay, so outline, harmonic analysis, then locally compact abelian groups, and then topics. So sticking to what the title is. All right, so we're all harmonic analysts. And a fundamental question that many of the people sitting in this room have asked is, okay, we take some function psi in some function space, typically it's L2 of some measure space, and then we have some projective or just unitary representation of some group, and we subsample that representation and we look at the orbit of this vector psi under that subsampling this representation. And we ask, how close is this to being an orthonormal basis? And there's a lot of words we use for close, like being a frame or a respaces or a Bessel sequence, or even something even simpler like being complete. I'm not going to get into all the definitions here that most of you know anyways, but just this is the motivation, is we're thinking, how close are we getting to an orthonormal basis? And some of the some standard results when we're talking about L2 of R, let's start with shift invariant systems. And I know in the audience, there's some of the world's leading experts on shift invariant systems, which I am not. So just stick to the knowledge that I have on this slide. So we're going to begin by defining a sequence of operators. So the first operator that we're looking at is the basic translation operators. You take your function and you just shift the inputs. And if we have some sort of function, psi, and L2 of R that's not 0, then the set of shifts of that function by the integers is an orthonormal basis for the closure of that span, if and only if this periodization function is 1 for almost all C. And there's lots of other sort of associated functions that you can have that say, hey, if this function has property X, then that means this set of shifts is some sort of generalization of orthonormal basis. Okay, so now let's build up and let's add on another operator, that of modulation. And so we just take our function and we multiply it by e to the 2 pi I gamma times our input, for gamma being some element of R. And then we ask this question, let's take a single non-zero function L2 of R, we translate it by the integers, we modulate it by the integers, and when is this system an orthonormal basis or something like an orthonormal basis? So one way we can characterize that is with help of the so-called Zach transform. So we take the Zach's transform, which is this function without the absolute value, and say, what are the properties of this function as we let X and C vary? And if it is pointwise AE equal to 1, the absolute value is, then we know it's an orthonormal basis. And then finally, we have multi-resolution analysis. So we're building up our very last operator, which is this dilation. So we're taking a function and we're either pulling the values up and shrinking in the mass, or we're pushing the values down and pushing out the mass of the function. So if you haven't seen an MRA before, then this is a lot of words. And if you have seen it before, then this is just the standard multi-resolution analysis definition. So we have a nested sequence of functions and some special function such that the shifts with respect to the integers form an orthonormal basis for one of these subspaces. And then if we have certain additional properties, then what we end up getting is the existence of some function psi that's going to be different than this other function that's called the scaling function, where if we take the integer translations and the integer powers of two dilations, then this thing is an orthonormal basis. And now if you notice in all three of these sort of classical examples from harmonic analysis, we are shifting over the integers. So I just want to give some quotes. Guido Weiss said in 2013 at SPE Optics and Photonics that the group that's really important for wavelets is the integers. And Carlos and Vicky said in their paper, shift invariant subspaces and LC groups, basically the important thing for shift invariant subspaces is the group ZD. So somehow the integers are really powering a lot of results that we have in harmonic analysis. Okay, locally compact abelian groups. It's fun and sometimes useful, not always really useful, but sometimes it's useful to study shift invariant Gabor and wavelet systems for L2 over different measure spaces. So we've already seen examples, of course, throughout these sessions on looking at L2, where we're trying to look at different sort of fractal measures and things like that. But here I'm going to be focusing more on groups. So something that has a Har measure, for example. But what do we do? How do we use these techniques that we know from real harmonic analysis if there's not an analog of the integers? So if we don't have a discrete co-compact subgroup. So I don't want to get into the explicit definition of a locally compact abelian group. It's a Hausdorff topological space and an abelian group where these two operations play well together. So the group inversion and multiplication is both invertible with respect to the topology. And then there's each point has a compact neighborhood. So these are basically the things that you do standard Fourier analysis on. So the really standard like Euclidean spaces, tori, integer lattices, finite abelian groups. What we'll be focusing on this talk are p-adics or vector spaces or the p-adics. And so these have a lot of very weird properties that are quite different than the elementary locally compact abelian groups that most people here are probably familiar with. And the important thing is this structure being a locally compact abelian group that allows us to do Fourier analysis, have well-defined translation and well-defined modulations. And if we have some additional structure, then we can also define dilations. So for example, it's standard thing to do is over RD, and we'll see that we can also do this over vector spaces over the p-adics. Okay, so why do we care? Before defining what the p-adics are, why do we actually care about them? These things serve as both an object of interest and also a tool in algebraic number theory. So if you've ever seen a result on finite dimensional Fourier frames that says, hey, if you take a submatrix of a prime order discrete Fourier transform matrix, then that is always going to be invertible. That comes from Chebotarev, and that result was actually proven with the help of the p-adics. And so the p-adics just come up as a very, very useful tool. There's also been a lot of work, in particular in Russia, on trying to figure out how to use the p-adics to do modeling of various phenomena in quantum physics and biology, in chemistry, and so on. But also, you know, we're mathematicians, so it allows us to sort of leave the comfort of the real numbers for new adventures. Okay, so what are the p-adic numbers? The p-adic numbers are just a completion of the rationals, just like the real numbers say are a completion of the rationals. We just have this absolute value and we take all the Cauchy sequences of the rationals and we fill in all the gaps. So we're going to start again with the rationals. It's just how we define closeness between two rational numbers is going to be different. So let's start with p of prime and pick any non-zero rational number r. By prime factorization, we have a unique way that we can factor out p from r. So r is going to be a quotient of two different integers, and we sort of can factor out the maximum number of p's from the denominator and factor out the maximum number of p's from the numerator and divide that out. So we have something of the form p to the nu m divided by n, where m and n are relatively prime and p doesn't divide m or n. Then the p-adic valuation of that number is you just flip the power of that P. So let's look at some examples. The 2-adic valuation of 2, well, 2 has 1 copy of 2 in it. And so we change that 1 to a -1, so the 2-adic valuation is 1/2. The 2-adic valuation of 4 of 1/4, well, 1/4 has -2 copies of 2. And so it becomes 2 copies, that's equal to 4. The 2-adic valuation of 7, well, 7's prime, so there's definitely no factors of 2 in there. And so that valuation is 1. Let's look at something a little more complicated. 5 divided by 6. The 2-adic valuation of that, well, there's no factors of 2 in the numerator. There's 1 factor of 2 in the denominator. And so this 2-adic valuation is going to be 2. So 2 to the positive 1. And then, so we have this way of defining a topology, a metric, a sense of closeness on the rationals. And we just complete that analytically to get the p-adic, just like we would with the reals. And actually, up to equivalence, these p-adic valuations and the sort of standard absolute value are the only absolute values that you can put on the rationals. This is a classical result from Ostrovsky. Okay, so we started with rationals, and then we built them up to get p-adics. The integers live in the rationals, and I'm trying to set this thing up of saying, hey, we need integers to do a lot of our arguments harmonic analysis. So why can't we just build up shift invariant spaces and Gabor systems and wavelet systems with translations over Z? And the reason is that Z is not discrete once we put this new distance on it. An easy way to see that is if we look at the p-adic valuation, so this would be the distance between p to the k and 0, well, that's going to be p to the -k. So there are integers that get infinitesimally close to 0. In fact, there are numbers that get infinitesimally close to all these different numbers. So Z is not discrete. So one group that we care a lot about are the p-adic integers, which is the completion of Z in QB. So it's kind of breaks your head because you're so used to thinking of the integers as being discrete. So the completion should just be themselves, but they aren't discrete in this new setting. And so we have these p-adic integers. What's kind of crazy and also is very hard, it's kind of brain melty to think about when you're so used to Euclidean space and elementary locally compact abelian groups, is that the completion of the integers with respect to this valuation is actually also equal to the unit ball. So if you take all of the numbers in the p-adics that have p-adic valuation less than or equal to 1, that is equal to the integers that have been completed. And it's also a compact open group. So lots of weird things that just very unnatural relative to Euclideans. So there's no non-trivial discrete subgroup of QP. And so the only discrete subgroup you're going to get is not going to be able to fill up the entire space. But there is a sort of canonical set, and I put that in quotes, but a canonical set of coset representatives of the p-adic integers and the p-adic numbers. And these things, they're spaced out very evenly. And so what a lot of people have done, myself included, is use this as a substitute for a translation group, but it's not a group because it's a set of coset representatives. Okay, so I slid in 2 pictures of fractals, even though this talk isn't about fractals, but I wanted to tie things into the official title of this session. So this picture right here is representing some of the very weird topology of the p-adics. In particular, these are the 5-adics. So all of the numbers, so these are just normal integers, and all of the numbers that are in a same green circle are all 1/25th away from each other. So with the 5-adic valuation, 0 is 1/25th away from 100, which is 1/25th away from 50, which is 1/25th away from 25. So all of these points are so balls, neighborhood balls are also equidistant points. So that's a little weird. There's infinitely many centers. And then everything that's in a blue circle is 1/5 away. Anything in 2 different blue circles, then you're getting to 1 away. So you end up having this this nice nesting that comes up, this very fractal-like nesting, and that's the topology. Okay, so what are the topics to discuss? So we're going to go back through these 3 classical topics in harmonic analysis and try to think about how we can kind of do these things over the p-adics. So we start with shift invariant spaces. And so this is a slide that I've put in because I want to tease or taunt some of these experts that are here sitting in this room to come up with a solution to this. So most of the methods that we have over Euclidean space or more generally locally compact abelian groups to characterize how close a set of shifts of a function are to being an orthonormal basis, like frame, respaces, Bessel sequence, so on and so forth, require that the set that you're shifting over is itself a group. So you have L2 over some group, and then you look at some subgroup, typically discrete subgroup, and then you use those for your shifts. So something like the p-adics, and there's lots of other examples, they don't have such a group. So there is a sort of way around it that, so my advisor, John Benedetto, in his his mathematical son, who's not his mathematical son, so his blood son, who also does math, wrote a paper together on wavelets over local fields. And what they did is they kind of generalized translation, being sort of inspired by the fact that if you take a translation operator and you conjugate it with a Fourier transform, you get a modulation operator. So they define an operator that's kind of like a modulation, and then conjugate that to get translation, something like translation, but it's not translation, but it does have a group structure. And there's been some work where this paper right here, where people have kind of taken some of these standard results from shift invariant spaces and applied these to these sorts of translations. However, these translations can do very bizarre things. And for a lot of functions, this translation will actually change the shape of a function. So it's like, doesn't have the same support size. It's unitary, but it's doing some weird things. So if you have this translation operating on a very nice function, it's fine, but it has some properties that are less than desirable. So my challenge is to sort of figure out how to make a theory of shift invariant spaces that uses actual translations that you can actually use over to locally compact abelian groups without lattices. So this is a challenge to those of you here who are sitting here listening to this, who are the world leading experts in shift invariant spaces. Okay, so moving on to the next topic, which is that of Gabor frames. And so I'm going to be giving a little teaser of some results that Vicky and I are almost done writing up. And many of you who have worked with Gabor frames might have seen what I wrote with the Zach transform and thought, okay, but we have all of these results using this thing called Berling density, and we can prove various facts about things that aren't lattices using Berling density. And so if you thought that, then you're correct. This is the way to get around it. And if you haven't seen Berling density before, the basic idea is you just take some sort of neighborhood, some ball, and you start growing out that ball. And at each time you grow out the ball, so you have a certain radius and you say, how many points in my shift set lie in that ball? And then you move the ball that radius around and you count up all the different places that you have a shift. So for example, if you are in the real numbers and then you have a ball that's of radius 1/2, an open ball of radius 1/2, they're going to be hitting like these integers a certain number of times. They have something like a radius of 1/4, then sometimes you'll have one integer inside and sometimes you'll have 0 integers inside. And you move these things around, and then you say, well, what's the largest number that lands inside that open set? And then we sort of divide by the area, and then you do the same thing, what's the smallest number? And you take these limits, and with the integers, if you play this game, then you end up getting that they have a density of 1, which makes sense because intuitively our gut says they're spaced out. They are spaced out at 1. And it ends up, you can very naturally sort of generalize this to a larger class of locally compact abelian groups. And here's an example of how to do it in the p-adics. And it ends up this set of coset representatives that I didn't define for you, but I just said there's a canonical class of coset representatives of the p-adic integers. This has density equal to 1. So this is kind of showing you in a Berling density sense that these coset representatives are like the integers. They're lacking the algebraic structure. And so it ends up that Vicky and I have generalized this result from Christensen, Ding, and Heil in the late 90s that basically says that if we modulate and translate a function, or we also, holds more generally for a class of different functions, then if we get a Bissell sequence, then we know the set of shifts and modulations had an upper density that was finite. And if we get a frame, then we know the lower density was at least 1. And so the little caveat here is this original paper uses some tricks from complex analysis that are not available when you're working over the p-adics, because the p-adics don't live inside the complex plane like the real numbers do. So instead, we sort of leverage some more algebraic tricks. Okay, and so the very last topic is that of multi-resolution analysis. And now we're going to be doing this over the p-adics. And so let's recall we have a multi-resolution analysis. It's a set of nested subspaces of L2 that go up to fill up all of L2 and intersect down. So they're just the space that's just the 0 vector. And we have some way of naturally moving from one to the other. And we're going to generalize this by saying, okay, now we're looking at L2 over vector spaces over the p-adics. And our dilation now, so before when we were looking at dilations for standard real vectors or over real space, we are looking at just multiplying by 2. And now we're just allowing multiplying by any invertible matrix. And so if we have this sort of very natural generalization of multi-resolution analysis, so we can do a standard multi-resolution analysis where we have a function that if we take the integer shifts, then it's an orthonormal basis for one of these subspaces. And we generalize this, the p-adics to say instead of the integer shifts, we're shifting by this set of coset representatives, or the vectors that are formed by this set of coset representatives. And we also have a looser version where instead we ask that those shifts by the coset representatives form a respaces. Again, it's just loosening up orthonormal basis if you aren't familiar with the respaces. So it ends up that there is a multi-resolution analysis for L2 of the p-adics under dilation by p. So here all we're doing is we're shifting by those coset representatives and we're dilating by powers of p. And you get a scaling function that is just the function that is 1 if something is a p-adic integer and 0 if it's not. So if you think of the p-adic integers, again, they're the unit ball, then this looks very much like the Haar MRA we have in the real case, because the Haar MRA, the scaling function, is the indicator function of the intervals 0, 1, and it's 0 everywhere else. Okay, so maybe this isn't too surprising. What should be surprising for those of you who have seen a lot, worked a lot with multi-resolution analysis, is that if the associated subspaces you get from that generalization of Haar are the only possible multi-resolution analysis that you could get for L2 of the p-adics under dilation by p. So for the reals, you have an entire range, like going from Shannon, Paley, Littlewood to Haar, and they're sort of extreme, and there's all these different cases. And in this case, there's literally only one MRA structure. Like if you want those nested subspaces, then it's going to look like this. However, on the flip side, that one MRA has infinitely many possible associated wavelets. So it's not just a trivial case where there's nothing to talk about because you still have infinitely many wavelets. It's just they're all associated with the same MRA, which is very different than the reals. And one such wavelet, which is going to again look a lot like the Haar wavelet, is we take the indicator function of the integers and we do a dilation and then a dilation and a shift of that, and then we subtract one from the other. So just like with the standard Haar wavelet. And some of these proofs are so similar, like you literally can just copy out, like you can literally just replace your R's with Q sub P's. And some of these proofs you have to come up with something very different, because when you start getting into work over the p-adics, you realize that there's definitely a lot of MRA theory that is built on the fact that the integers are a group. And when you no longer have a group, then you have to do a little bit of extra work for some of the parts of the proofs. And so this is something that actually comes from my dissertation, was this work on using a Quine-Cook's matrix for dilation over the two adics. So the Quine-Cook's matrix, if you aren't familiar with it, is the matrix that's 1, -1, 1, 1. And if you think about it geometrically, what it does to vectors in R2 is that it just rotates them and then isotropically scales them. So it's a very unique matrix because it has this, it's an integer matrix that has a very, very nice like geometric interpretation. That's not just scaling and flipping. Like it's this nice sort of rotation. It has something really cool it's doing. Also 1 and -1, those are numbers that are in every field. And so you can use this matrix to do things in lots of different regimes. And so I'm just going to look at the inverse of that matrix. And I'm going to define a wavelet that should look a lot like the Haar wavelet, but now I'm taking the integer function of the square of the integer. So that's just a vector where each of the entries is a two-adic integer. And I feed in a of x, and then I feed in a of x minus 1/2, 1/2. Then it ends up that if we do shifts by the coset representatives and dilations by the powers of this matrix, this Quine-Cook's matrix, then we get an orthonormal basis for L2 of Q22. And that wavelet is actually associated to a multi-resolution analysis with respect to scaling by A. And it has scaling function that's just like with Haar, it's just that indicator function of the two-adic integers squared. But what's kind of weird is that this multi-resolution analysis structure is the tensor product of the 1D Haar multi-resolution analysis structure. Why this should be surprising is that these 1D structures, if we were to think about what happens in the reals, they're just scaling by 2. And then this structure is scaling by the Quine-Cook's, which in the real case, you're like dilating and rotating. And so as a matrix, it's kind of hard to wrap your head around that this matrix here, 1/2, 1/2 minus 1/2, 1/2, is somehow related to tensoring something that's just a single 1/2 and a single 1/2, and tensoring that along the 2 dimensions. That's definitely not the case in the reals, because this is clearly not a diagonal matrix. And here's my second little fractal slide that I threw in there. If you want to do dilation by Quine-Cook's and shifts by the integer lattice in R2, there's this fun paper from Groening and Marich in 1992, where they build up a multi-resolution analysis structure. And this is a diagram of what the wavelet looks like. So this is a 1 and then a -1, and then everything is 0. So you get this twin dragon is the support. So this is clearly a lot more complicated than just a function that basically is built off of the support of the integers, the two-adic integers. So you have these little fractals that are coming up. And I just want to end with saying that if you can use MRA to build up these things called bi-orthogonal systems. And it ends up that you're still, if you loosen up to Riesz MRA, you still only have the Haar MRA. There's still only one structure of these nested sequences, but you can get bi-orthogonal systems from it that aren't orthogonal. So that might also be surprising to you if you're familiar with these MRA structures. So in conclusion, I mean, I know some of this stuff was maybe a little complicated without explanation, but I really wanted to just kind of touch on a bunch of these topics. And just to not forget the latticeless groups. They deserve love too. They can be fun to play around with, and it can be a nice little like mental exercise and help you understand too more deeply what's going on with the reals, because you see how much is dependent on the integers and how much isn't. And thank you again for the invitation. And yes.
So thank you very much, Emily, for a beautiful talk. Are there any questions from the audience? I do have a question, if nobody jumps up.
I just wanted to say that I thought it was beautiful, Emily. Thank you.
Okay.
I have a question for the on your slide 21, but it's not important that you bring it up. I mean, it's just when you define the multi-resolution analysis, you say that A is just the general invertible matrix because for multi-resolution analysis in the classical sense, you need it to be expanding, right?
Yes, I mean, this was already just a lot of text on a slide. So there's things that are, and also, you know, you don't just want that it's expanding, you want that it plays well with the system that you're shifting by. So,
exactly. This is what the next question I had, because I mean, the examples that you put on were all respecting these two things. And then I wanted to know if it was hypothesis or it was just the examples you put. No, okay.
Well, I should say they aren't, so yes, you've got these, and this, the reason we do this inverse is because in the two-adics, multiplying by 1/2 is the expansive thing.
Yeah, okay.
Not multiplying by 2. And so this is why we're playing with this matrix rather than, and the reals you would have, the base matrix is this because that's expansive in the reals, whereas this is expansive in the two-adics.
Yeah, but it's the same because you go forward and backward. So it doesn't matter really which one you use.
Right.
Okay, thank you very much. I really enjoyed the talk. Are there any more questions?
Yes, I think somebody in the chat asked a question, but I have another question.
Sorry. It is always hard with Zoom.
Yeah.
How is the L2 norm defined in the p-adic spaces? Okay, so all of the functions that I'm dealing with here, and again, I was just doing that shallow little touch, because you can talk about function theory on where both the domain and the codomain are p-adics, and you can talk about function theory where the domain are p-adics and the codomain is complexes. And so I'm living in the world where all the functions are complex valued. And because the p-adics are a locally compact abelian group, that means we have a Haar measure. So we have a well-defined way of doing LP theory. Because this is always in this talk, there's lots of interesting work done other places, but in this talk, all the functions are complex valued. And so you just define it with respect to the natural Haar measure that comes up from the fact it's a locally compact abelian group.
Guys, yes. My question, Emily, was can you recall that you say you want a theory of shift invariant spaces with real translation without using lattices?
Yeah, so
I didn't quite understand what you want.
Yeah, so what would be nice?
Yes.
Yeah, what would be nice would be having something like you have some non-zero function in L2 of the p-adics, and you want to know whether or not the shifts of that function with respect to, say, this nice set of coset representatives that I didn't explicitly define, but this set that is, you know, very evenly spaced out and is in a group, but is kind of like a group because it's a set of coset representatives. Like, can you have results that say something like the periodization function or the brackets or the fibers or all of these different techniques are like really built, like really need the fact that you're shifting over a group. And is there a way to sort of change things where you shift over something that's not quite a group, but is close in some sense? Because it seems like everything needs the group structure.
But you write here lattices, or do you mean groups?
In this case, the same.
Yeah, so by that I mean, yeah, that they don't have a
Discrete group.
co-compact discrete subgroup.
Oh, thank you. Very nice talk, Emily. Thank you.
I have one question before. So when you said that the only multi-resolution analysis that you get is the HAR one, but then you have infinitely many HAR. I mean, is there any distinguished HAR function that you could really say? I mean, are all of them HAR functions, or you can you did single out one in the Z2 case, right? That really looked like.
Yeah, so that one, that comes from a paper by Kozyrev in 2002, and he actually came up with sets of wavelets that work for all of p-adics. And of course, this one is the one that is most HAR-like to those of us who know the HAR wavelet over the real line. So that result came first, and it was only later here in this paper, 2010, from Albaverio, of Dokimova and Skopina, where they proved that there's only one MRA. So first, people were just kind of finding lots of different generators. And I should say, Kozyrev's paper, or also just in general, the other wavelets you get they're not equivalent to the HAR, like they do give you different systems, but they're somehow similar. Like you're still doing some sort of linear combination of, I mean, I guess you have to, right? A linear combination of the scaling function. So it's still kind of HAR-like in that you're getting these sorts of that type of function. But and as I mentioned, this later result that I have with Maria Skopina is that we can now also get, bi-orthogonal wavelets out of it. So even though we can't get a non-orthogonal MRA, like the scaling function, we can't get a scaling function that's going to be a respaces but not orthogonal, but somehow that we can use that to generate non-orthogonal wavelets. So there's some freedom in the choice of wavelets that just, I don't understand exactly why that happens.
Thank you. It was really nice talk. Fascinating.
Sorry, I just realized my sister's in the background with my nephews.
Very far, we don't see her. Okay, Emily. Let's thank Emily again. And we actually have a break of about 8 minutes before